So, almost there. There we go. So last week you probably remember all this fun stuff. Talking about stress and strain in 2D, and how stresses in multiple axes are related to one another via Poisson's ratio. Um, uh, I did in there a little bit of thermal strain, how it's independent of all this stress related to stuff. It just adds on to it. Um, it's a little bit, this is a little bit ahead of linear algebra here. Don't really worry about it too much. It's really just a shorthand way of writing these equations out. You can also think of if I take each row here and multiply it by the column, so like that gets multiplied by that, gets multiplied by that, that gets multiplied by that, and I add them all up, I get the same expression that's there. If you want to know how I get from point A to point B, but you don't really have to know that part, at least not right now. Just to hang a little bit for later. So that's where we were last week, and this kind of wraps up the basics of 2, and I mean it's not that great a stretch to put this into 3D. Right? It's just you just add another stress term here for isotropic materials. This kind of wraps up 2D axial stress and thermal expansion. So if you have any questions on this, well, say something about it because we're moving on. Oh, actually, there was one other thing I wanted to talk about with this. Almost forgot. Something called Saint Venant's principle. This is more conceptual than mathematical. What's going on over here on the right is a visualization of stress. It's something really cool that you can do with certain kinds of materials and sensing techniques. Is that I think it's ultraviolet or infrared. I forget the exact kind of sensing, but you can actually visualize stress distributions in certain materials. Like I think this is a kind of plastic. No, actually, sorry. This is just visual light. This is a certain kind of clear plastic, and as you apply a stress to it, it'll actually change the optical properties of the material, which is really cool. And it also means that you can start to, if you look at the light that's being refracted through the material, you can actually get an idea of how stress changes throughout it. You can correlate this with how much strain is there too. It's a really, really neat thing. But what does this give us? So if this is how much stress is changing, if you see a change in color with the intensity of how quickly stress is changing, what does this tell you about this middle region here? Is it relatively uniform, constant stress, or is it rapidly changing? Is it varying, or what? Looks uniform to me too. So this is pretty constant. You might say this is kind of constant down here. This is sort of constant. What about like here near the end? What's that doing? Yeah, it's not constant. There's a lot of change. In fact, there's some kind of weird stuff going on because like if I draw a little line to kind of outline that area there, this part here and this part here are perfectly clear, meaning that there is no stress in them. They're just regular pieces of plastic. It's like you're looking through a window. There aren't any colors there because the index of refraction hasn't changed due to stress. And then as soon as I get away from those, I get this weird like fluorescent region kind of thing going on. It's somewhat psychedelic because the stress is changing so quickly. This is a result of something called, this is kind of encapsulated rather in St. Venant's principle, which is to say that the amount of stress that's near where a load is applied depends on how that load is being applied. Kind of like how we've been saying that we're computing the average normal stress, and average shear stress, and all these average stresses. That's kind of the best we can do right now because things depend so much on how a load is applied. So like this is a very concentrated load. It's not like I have, say, this rock sample and I'm pressing down on the entire top surface evenly. It's as if I was poking down right in the center and applying all, or rather as much load as I could to a very, very small point. And as you can see with these test specimens, that dramatically changes this, it's called the actual stress near that point. Now when we get far away from that, everything's kind of uniform, straightforward. We could probably figure out what the stress is in that bar right there, no problem at all. It would probably correspond pretty well to what we've been doing. But it's only once you get away from those, quote, end effects. However, by corollary, this also means that once you get away from those end effects, so like after you get away from there, it doesn't really matter what load's at the end. I mean, I could have a point load here. I could have a distributed load here. I could load that end however I wanted. This stress would stay the same. Why would that be? Or does that not make sense? Does that make intuitive sense? Does it not make intuitive sense? I put it this way, I'm not saying why would that be in a, tell me the like molecular workings of materials. It's more like, does that conceptually make sense, or does it conceptually not make sense? Okay, I see enough of shrugs / nodding and heads. I'll take that as assent unless there's vocal dissent. Okay, cool. That's nice. That's a nice logical conclusion then. The stress away from a load is relatively independent of the load, and we can kind of replace that loading with something more convenient if we want to. For example, if I say take a section through here, I can say, well, I don't have a point load now, I'll have a uniformly distributed load across this section because it doesn't matter what the load distribution is anymore. I can assume that it's independent of however it was applied. All right? However, that works well if you have a uniform cross section. If you don't, say like you have this hole in the center, there's all kinds of weird crap going on here, right? While the stress leading up to the hole's relatively uniform, the stress around the hole, like here or around these notches here, gets weird. It starts to increase and cause what's called a stress concentration. So one way that I think's half decent of explaining like the concept of stress concentrations, because half of the importance of these things are just being able to get an idea of where they might be in the first place, being able to identify them so that you can be able to identify critical locations so that you can apply the proper analysis at those locations. So one way that you can kind of think of to identify them is first to think of stress as water going through a pipe. Stress in a material as water going through a pipe. So I have my fluid flow moving through here. say if I drop a particle here, I can kind of watch it go along, go along, go along, and it goes out the other side of the brick. It's kind of like if you were dropping sticks in a stream or something like that. You're watching them go through a bridge. And if there's nothing to disturb the flow, so there's not like a hole in the center or something like that, or like a curve right here, like there's nothing like that to disturb it, everything will go nice and straight. And you might imagine that this is kind of like that beam to that specimen to the far left. It's just a nice uniform cross sections. Everything's fine. But if you put a hole in the center, the flow now has to go around it. You might think that there's, in terms of materials, the same load is applied here. Wow, there's a terrible arrow. There's the same load as here as is here. And it has to, and the same load is applied at every single cross section. Every single cross section has to react to that same load. Question is just what it has to react it with. So, and how well it can transmit that from section to section to section. So in this center area, not only do we have a reduced cross-sectional area, which you computed in the last homework, I think, or this homework rather. No, it was in the last one, and that's going to increase the stress. But you also have what's called, but you're also kind of forcing the transmission of this load to take a different path, and that's going to actually increase your stress by more than just what you'd get by finding this new cross-sectional area. So say that A has twice the cross-sectional area of B. That means that our stress at B would just be twice as much, right? But it can be a lot more, depending on the size of this hole relative to the width of the block. So, in other words, how extreme that change in flow pattern is, and how much and how that load has to be transmitted between different sections along the block. Your stress can actually be several times higher than your average stress. So in this case, this is a chart that you can find on page 108 of your book if you look, if you have it. What this chart gives you is something called the stress intensification factor, which is, if I had a thing, which you can use to find the maximum stress at a stress concentration based on what you compute to be the average stress at that point. So if I'm looking at this cross section here, it has some area A, and I know the load P. Sigma average would just be my usual P over A gig. But because there's a stress concentration there, because there's something diverting that flow, if you will, because there's some weird geometry or whatever, I need to effectively multiply this by K in order to get the maximum stress that's occurring at that cross section, because that's what's going to cause it to fail, and that's what I need to compare to the ultimate stress or the yield stress, and you apply the factor of safety to it and whatever, because that is the highest stress at that cross section. So, like we were saying before, if this cross section, say here, has twice the area of A, the average stress is going to be twice as much. But then, depending on the radius of the hole, which call it the maximum stress could be 6 times the stress that's in the rest of the stress that's in the rest of the specimen. So this is a really big deal. and this isn't just true for things with holes in the middle. This applies to notches. It applies to corners. There are a whole lot of different cases. And on page 108, you have a couple of tables for stress concentration factors. They're kind of scattered throughout the rest of the textbook. If you ever need one of these charts for like a test, don't worry, I'll give it to you. You don't have to like reprint it onto a page or whatever, but be able to but know that this will show up on homework and you'll probably have to find it. All right. All right. So, so by notches, so you know, actually, I'll just do that. So in terms of other things where this would come into play, so if you had something like that, talked about that. This is, so all these different shapes, you might call all these shapes have one thing in common. It's that how the load is transmitted, how the stress is transmitted through the structure changes between cross sections. And because it's changing between cross sections, it means that there's a stress concentration wherever that occurs. So here, 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 and here. And the more abrupt that change, the higher the stress concentration. That's the general rule of thumb. So on a practical note, if you make all your changes in in shape and diameter relatively gradually, the effect's relatively small. Is that always easy to do? Not at all. So that's why it's such a big deal. Oh yeah, there's another stress concentration chart for the for one of the other cases that I had. Note that as R goes to 0, the stress concentration factor goes towards infinity. So it's kind of a big deal. All right, I already talked about this, so I'm not going to worry about it because we're moving on to the wonderful world of torsion. Do you guys have any questions on normal stresses? Okay, cool. So torsion, yay torsion, yay torsion, yay torsion. This is a dynamometer for wind turbine generators. Which call a dynamometer is a machine that can apply a torque or test how large a torque's being exerted on a machine, a generator, an engine, whatever. Here it's really freaking huge because it's like a 2 megawatt turbine, and then so the generator has to be able to exert 2 megawatts of power on this thing. It's really cool, especially because you can adjust forces on it, stuff like that. Anyhow, so torsion. So from statics, you probably have heard of moments. You've heard of moments. You've probably heard people throwing like torque and all that kind of crap around. Don't get confused. They're really virtually the same thing. It's almost semantics that separates them. We're going to be taking a whole lot of things that appear to be moments, and you're right. Just a force act in a distance from an object's center of mass, or in our case, often from an axis of rotation. A torsion is a stress that results from that. So one usual example is, say you have a shaft with some gears on it. you can apply a moment. You can apply a force at a gear tooth which creates a moment around the shaft, right? So the shaft wants to spin now. But that in turn is also going to generate a torsion or torsional stress in the shaft as it tries to resist that motion. So that's a lot of the language that we're going to be using. We cool with the language. Cool. We cool with the language bit. Cool. So I won't really bother with this, and this is just another example of what we call moments generating torques and all of that. If we don't have to do it, I'll move forward. So, why, right? Why it's called whole? Why do we have these stresses? And it starts out with just a definition of a torque or a moment, really. This is called whole. This is so if I take the integral of r with respect to a force on an element, say, I'm looking down the end of a shaft, and say here's the center. And I look at a little element here that is a distance r away from the center, and there's some force F acting on that. I could find the moment generated by that force acting on that element that distance away from the center of the shaft, right? Just r. This is a differential force. It's a very, very small component of, say a total force acting on this. So if I have a whole bunch of these elements, rather like all the ones in the shaft, so I have to say that I'm trying to turn this shaft, it means that there's some force distribution across the inside. You following me here so far? And I can kind of look at that force distribution, add it all up, and get the total force I'm exerting on the shaft. If I multiply each little element has a force acting on it by whatever distance that force is acting from the center of the shaft, I can get a moment for each of those, add them all up, and I get a moment or a torque. We cool with that? Cool. So if I start with that, well, if I'm looking at little differential elements, each differential element has to have a certain area associated with it. And if each one has an area associated with it, that means that it has a stress. Because I can say, well, the FDA, right? It's just the differential of force over area. So I can do a little substitution for this force and recast the expression for torque in terms of shear stress, because the force, if I'm creating a torque, I'm not on this bar, I'm not pulling on the bar, I'm twisting it. So my force is in plane with a cross section of the bar. So I can say that it's a shear stress, and I can say that torques cause not just stress, but a shear stress. Torsional stress is just another way of saying shear stress. So that's where we're kind of starting out. All right. Cool. So what does that look like? And it actually looks really, really cool. So this is a rock that's being twisted, and I think it's failed. And you can actually see the grain, which is called the grain of this rock, is twisted. It's actually, it's called the shear stress in the rock has actually deformed the surface of the material. But this is just the but this is just the surface. As you might imagine, I mean, as you go down from the surface towards the center, that how this looks might change. Like if I was at the center of the rock, do you think there'd be any sort of deformation? If I'm just twisting it, would the center of it change?
No.
Why? What do you think?
The center would be, if it was rotating, then stuff would
Stuff would rotate around on the center. Yeah, intuitive, which call it intuitively. If we're just twisting a rock, if we're twisting whatever, the center line's the point that doesn't move. The outside's the point that moves the most, and everything in between kind of moves relative to how far away it is from the center, right? So maybe so if we kind of link that up to stress, kind of the same way that normal strain and shear strain were related to stress, maybe the amount of stress here is then also related to how much deformation there is. So maybe there's some internal shear stress distribution caused by torque. So in order to do this, we have to look a little bit more at how these deformations work. I forgot to bring a water bottle in today. Dang it. Oh well. Okay. So this is essentially what we were looking at before. One thing I want to note is that these cross sections, you compare them here and here, even though these straight lines that run longitudinally down the sample have twisted due to the torque that I've put on it. Excuse me, which is for reference going that way. That blue looks really nice. Those even though those longitudinal lines have strained, the lateral lines have stayed parallel, and furthermore, at least here, have stayed about the same distance apart. Is now that last bit, that everything stayed the same distance apart, so this length is still the same as this length. Does that seem like a good assumption? Does that seem intuitively correct? Why?
because there shouldn't be that much stress being applied in the opposite direction of force.
Okay. So what you call this is you're just torquing it. It's pure shear. There's nothing going this way. But another way of thinking about this is you guys ever scrunched up a water bottle, like screwed it, hit it together, and blown the cap off? So what happens to the length of the water bottle as you screw it tighter and tighter and tighter and tighter and tighter? It shrinks by a lot, right? Hey, but that's because you've gone way past this yield. You've twisted the bottle several times around itself. The deformations on the order of, like, I don't know, 6 pi radians or something like that. It's several revolutions, and that's what and by doing that, if I start wrapping these longitudinal lines around and around and around, the total length of the line has to stay the same, so the total length of the specimen has to decrease in order to compensate for that. If these deformations are small, however, which is typically true for more for when we care about when things fail. It's a water bottle. We don't care that the fact that it's yielded it yielded within the first, like, 5 degrees. If these deformations are small, which is the case for most everything that we care about, then we can assume that the length isn't going to change that much. In fact, we can ignore the effects of of this on length for the same reasons that you said before. We're not exerting any stress in the longitudinal direction. Therefore, we can expect the length not to change very much or really in any sort of significant way due to a pure torque. And it's the same for effects on diameter too. In the extreme case, if I really twist that water bottle down, I can see a change in diameter for the same reason. I'm trying to fit all this material into a different space, and so the diameter has to change in order to compensate for it. However, if we assume small deformations, which is a good assumption for most of the materials that we're working with, then we're fine. And we can assume length and diameter not to change due to an applied torque. All right, we happy with that? Wait. All right, so now we have a deformation. Now let's look at. But yeah, almost forgot. And everything that I just said is only valid for, again, small deformations and circular cross sections. If you have squares or other irregular cross sections, none of that really holds. But for us, circles are a good place to start. So we're staying with that for now. Also, most of the torques that you have to deal with are on circular cross sections because shafts are mostly circles. So it'll work for most things. All right. So if that's how it deforms, now let's kind of look at a little bit more of the stress. So if I simplify that last thing down into a cylinder stuck on into some sort of fixed boundary, I can draw a line down it and kind of track that line if I throw a torque on it, and I can start to find some angles and all that and all of that jazz. As we said before, this is probably a shear stress because I'm applying a force kind of parallel to the cross section. But another way that you can look at it is this. So I just moved this point A around the around the shaft just a bit, right? So if I cut out a little stress element from the shaft, say right here-ish, if I cut that out and looked at it and its next door neighbor and kind of walked that back down to the start here, each one of those elements is moving different than its neighbor. You might say that each one is trying to resist the motion of its neighbor, because back down here, stress elements haven't moved. There's no stress where there's no deformation. That's Hooke's law, right? But here there's a lot of deformation, relatively speaking. So there's a lot of stress. And each one of these elements is trying to resist that change along the length of the rod here. So you might think that if I have another element, say like here, for that guy to resist the deformation of, oh, that was strange. For that guy to resist the deformation of this element here, the only way that it has to do that is by shear stress, by applying a force parallel to the face of its next door or neighbor, of the neighboring stress cube. Does that make sense? So by that same, so by that sort of an idea, we can say without question or approximation that a torsion definitely causes a shear stress because of how it's deforming the rod. So based on that, we can try to find stress. So this should look familiar from last week, which called when we talked about shear strain and how it's related to shear stress by the modulus of rigidity. We said that shear strain is kind of the angular deformation of a stress element. So it starts out with these nice right angle, which called nice right angles. If normal stress deforms this way, which called deforms in a linear fashion, shear stress deforms kind of like an angular fashion. So a good measure of it is an angle in radians, always in radians. So if we can measure shear stress by angular deformation, maybe we can come up with a similar sort of idea for a rod. But let's kind of mess around with this first. This is a very general case of shear strain. So the element's not really constrained in any way. However, imagine that this is part of the rod that we had before. It's just an element on it, and I'm twisting it. Is there anything, and this is my original element here, and I'm applying a torque like that. What sides of the element are going to deform and what sides are not going to deform? Which ones are not going to move? Which ones are going to change direction or shape, and which ones aren't going to change direction or shape? What do we say was the same before and after, and what was different before and after? Okay, so diameter and length are the same. So if this is the length direction, if you will, so this is the longitudinal direction, is the distance between these two sides going to change? Say again? No, it's not. So these two sides should stay flat and parallel to one another, using our small angle approximations. So instead of this more general example here, what we're going to see is something more like this. Where if I drew it in red, where the red is our original element and the blue is the deformed element. So it's as if I had two ends of a book and slid one up. We cool with that? Cool. So maybe if I take that idea, throw it at a rod. So let me redraw that one there. Okay. So I have some sort of fixed boundary condition here. Have rod, throw torque on the rod. Torque. if I drew a line on it from one end to the other for a rod of length L, say, I could kind of track the motion of that line as it deformed, and I can find some angle of twist, or some deformation there. So if I drew an element on top of that, so if I had some undeformed element here, actually I had it in blue, I had it in red, that the top, the top of that guy has to move with the deformation. So it moved up by yay much here, moved up by yay much to further along. So there's more twisting the further along you go, just following this line, and I end up with some deformation like that. So if that's the case, I should be able to just measure the angle that the top and the bottom have skewed by, and that should give me my shear strain. So what angle would that be?
Same angle?
As same angle as what?
Is that theta?
Phi, but yeah. If the top and the bottom of the element kind of follow how the rest of the rod is deforming, that means that the strain has to be equal to what's called the angle of twist of the rod, or how much the rod has twisted in response to the torque, how much it's deformed in response to the torque in an angular sense. So here that means that our shear strain must be equal to the angle of twist. So great, that means that we are rocking and rolling. And if we run some math, put my lines back on there. That means that gamma, shear strain at any given point along the rod. How do I want to say this? Yeah. It's called the shear strain along the rod is dependent on, if this is a center line, has some radius r. This is an angle phi. Yeah. Yep. Exactly. That's that. It's dependent on the radius times the times the angle of twist. This is so the greater the radius, the larger this deformation at the end is going to be, right? As well as length. So that's it's called. I go into more detail, but we're almost out of time. So that's it's called. So that's the way that we can measure shear strain at any point in the rod. Because if I take my R to be less than, so say that like this is a 5-inch rod, 5-inch diameter rod, I could take my R to be any point inside of that rod, and I could find the shear strain there. I could also look along the length and find my shear strain in there. It's all it's real generalizable. So if I have that, this will be the last thing I do. I can take I can take it and kind of work my way back to this. So if I have, here we go, rho would be he's some radius inside. If I had a circle, rho would be to some element here. C would be my radius. Where was I? Here for L. If I wanted to find the maximum shear stress, it'd probably be on the surface, right? If it's called the larger this value is, larger the radial location is, the higher the shear strain would be, should correspond to higher shear stress. So if I say, so if I wanted to find out what the maximum is, and say, see that, sorry. How do I want to say this? I want to say, yeah, I can set up a, which I can set up a relation where that's the general form of shear strain for any point inside. We said that the maximum should occur on the outside, so that's that. So that's that. Expression there, just placing the the radius to a point inside of the cylinder to the radius of the cylinder itself. I can cancel a bunch of stuff out, and I end up with this expression here, which, if I don't want to go fast on this. I'll end. I'll end with this thing then. Which, based on this guy, I can say, well, if the shear strain at any point inside of a cylinder is a linear proportion of the maximum shear stress in that body, I can then finally get to the stress distribution that we were talking about to begin with. So this kind of confirms our intuition. At the center, when rho e equals 0, the shear stress is 0, and it'll build linearly until we get to some maximum value at the surface, at the surface of the cylinder. So tomorrow we'll talk about translating this into stress, or Thursday we'll talk about translating this into stress. In the meantime, are there any questions? Great. Thanks for stopping by. And grab a cookie before you leave.